we have studied about propositional logic and predicate logic. We have also studied about resolution principle, and we have seen the use of resolution principle in prologue, how logic is used in prologue. And today we shall see how predicate calculus or predicate logic is made use of in verification of programs. Now, when you write a program, you do not know whether it is correct or not. You will test with some test data, but for the given test data, if the program works correctly or it gives you the correct output, you cannot say that it is always correct, because some other input it may give a wrong value. So, testing only points out if there are errors, and even if it runs correctly, it does not mean that there are no errors. You could have errors, and for some other input it may not work properly. It does not tell you the absence of errors. If there are errors present, it will point out, but it does not point to the absence of errors. So, when you write a program, it is better to prove that it works correctly, and how you are going to do it with predicate logic, that is what we are going to see today. But again I want to tell you that we are going to explain this principle with just a simple example. For very large programs, this sort of a method may not work because it is too much involved. For small programs you can use this method, but for very large programs testing is the only possibility, and if you test with proper data, you have to assume that the program works correctly. Now, for simplicity's sake, I shall take flowchart programs, though it is a very old concept. I will take flowcharts. So, what we are going to see is verification of programs today, and we are going to consider flowchart programs. Now, let us consider a very simple class of flowchart programs. We distinguish among three types of variables. The program has to read something, and they are the input variables, and during the execution of the program it will use some other variables, they are called program variables, and it will output something, and that is called output variable. So, you have some input variables, say x1, x2, xa, an input vector which consists of given input values, and therefore, it never changes during the computation. These are the inputs. A program vector y bar which consists of variables y1, y2, yb, these are called program variables, which is used as temporary storage during the computation. And then you have some outputs z1, z2, zt, an output vector z bar consisting of z1, z2, zc, which yields the output values when computation terminates. Now, the inputs are defined over input domains. We have to specify the input domains. Similarly, the program variables, each one will have a domain on which it is defined, and then there is a output domain where on which the output variables are defined. We also distinguish among three types of non-empty domains: an input domain dx bar, a program domain dy bar, an output domain dz bar. Each domain is actually a Cartesian product of subdomains. See, you have variables x1, input variables x1, x2, xa. So, each one will have a domain dx1, dx2, like that dxa. The Cartesian product of that is defined as dx bar, the input domain. Similarly, the program variables are y1, y2, yb. Each one will have a domain dy1 for y1, dy2 for y2, and dyb for yb. The Cartesian product of that is defined as dy bar, the program domain, and there are z1, z2, zc are the output variables. So, each one is defined over a domain. The Cartesian product of that is defined as dz bar, the output domain. So, you have 3 domains: input domain, program domain and output domain. Now, we shall consider simple program statements. We distinguish between 4 types of statements. The start statement, which is start, and then the y bar is assigned f x bar, that is the program variables are assigned some values from the input variables, where f x bar is a total function mapping dx bar into dy bar. This is the technical way of. So, initially you start and you have a small assignment statement where y bar is assigned some values depending upon the x bars are the input variables. Then you have assignment statement. It is y bar is g x bar y bar, that is g x bar y bar is a total function mapping dx bar into dy bar into dy bar. So, depending when the program control reaches this point, depending upon the values of x bar, which is never changed, and the current value of y bar, that is the values of the program variable y1, y2, yb, new values for the program variables y1, y2, y3 up to yb are assigned, and this is a total function. And you have test statements. You have t of x bar y bar, where t x bar y bar, this is the same as this t, this is the same as this t. It is a total predicate over dx bar into dy bar. There are 2 outlets. Depending upon when the control reaches at this point, depending upon the value you give for x bar and y bar, or the value of x bar is unchanged, and when the control reaches at this point, y bar is has a particular value. Depending upon that, this predicate is evaluated and it will take the value true or false. There are only 2 exits, there is no exit here. This true exit exists like this. If the predicate is true, you take this exit. If the predicate is false, you take this exit. Then you have a halt statement. Finally, after the computation is finished, you arrive at this point. Then the output variables are assigned some particular values from the input and the program variables. It is h x bar y bar, where h x bar y bar is a total function mapping from dx bar into dy bar into dz bar, and then you halt. A flowchart program is simply any flowchart diagram constructed from these statements with exactly one start statement, such that assignment or test statement is on a path from the start statement to some halt statement. You may have more than one halt statement, but usually there is only one start statement. In other words, flowchart programs are not allowed to include dead end test statements such as this. That is, after performing this test, again you go here and keep on performing. You are not supposed to get into a loop like this. So, a flowchart program consists of start statements, assignment statement, test statements, halt statements, and every assignment or test statement occurs in a path from a start statement to a halt statement, and you do not have dead end loops like this. Having, you know what it is, you must have been very familiar with what is meant by a flowchart and so on, but still I am repeating all these things of which you are very familiar. Now, how do we make use of predicate logic to prove that a program which is given in the form of a flowchart is correct? It does what you intend it to do. Now, given such a flowchart program P, you are given such a flowchart program P and an input value psi bar belonging to dx bar. So, you are taking a particular input psi bar for the input vector x bar. The program can be executed. After taking the input psi bar, the program is executed. Execution always begins at the start statement by initializing the value of y bar to f psi bar, because the first statement, if you look back, is y bar is assigned fx bar, right. By initializing the value of y bar to f psi bar and then proceeds in the normal way, following the arcs from the statement to statement. Whenever an assignment statement is reached, the value of y bar is replaced by the value of g x bar y bar for the current values of x bar and y bar. That is what I mentioned to you. Whenever a test statement is reached, execution follows the true path or the false path, true branch or the false branch, depending on whether the current value of t x bar y bar is true or false. The value of y bar is unchanged by a test statement. If the execution terminates, that is, if it reaches a halt statement, z bar is assigned the current value, say zeta bar of h x bar y bar. When it reaches a particular point, x bar and y bar, x bar is never changed, y bar will have a particular value when the control reaches that point. Then h of x bar y bar will give you some particular values that is assigned to zeta bar. We say that p psi bar is defined and p psi bar is equal to zeta bar. Otherwise, this is the output, this is the input. Otherwise, if the, that is, we can say it like this, if the execution never terminates, we say that p psi bar is undefined. In other words, the program P should be considered as representing a partial function z bar is equal to p x bar mapping dx bar into dy bar. That is, given a particular input, you get a particular output. Okay. So, the input should belong to the particular input domain and the output should belong to the particular output domain, and they are related by this p x bar is equal to z bar. So, if you take a particular input psi bar, you get a particular output zeta bar, and they are related like this. Psi bar belongs to x bar, the input domain, and then zeta bar is the output and it belongs to the output domain. Dx bar into dz bar, this is dz bar. Consider a small, let us take a particular example and see what happens. I will come back to this slide later. Look at this. This is a small flowchart program, and what does this do? Start, and you are having two input variables x1 and x2 and two program variables y1 and y2 and two output variables z1 and z2. So, here there are two input variables, are x1, x2, program variables are y1, y2, output variables are z1 and z2. So, initially when you start, y1 is assigned the value 0 and y2 is assigned the value x1, and next you go to the control statement y2 greater than or equal to x2, and if it is true you take this path. if it is true you take this path, and y1 will be assigned y1 plus 1 and y2 will be assigned y2 minus x2, and you go here. If this is false, you take this path. In that case, outputs z1 and z2 are assigned the values of y1 and y2, and you get the Hall statement. So, the test statement is like this here: y2 greater than or equal to x2, and if it is true, the assignment statement y1 y2 is assigned y1 plus 1, then y2 minus x2, and then you go back here. If it is false, z1 z2 will be assigned the value y1 y2, and then you halt. Now, let us execute this program for a small number, then we will know what it is. Take the value of x1 is 16 and x2 is 5. So, what is the value of y1 and y2? The first time you reach your y1 is assigned 0, y2 is assigned the value of x1. So, you get this. Then you reach the test statement, is y2 greater than or equal to x2? Yes. So, you take the true path. So, you add 1 to y1 and subtract x2 from y2. So, you get this. Then again the control reaches the test statement, is y2 greater than or equal to x2? Yes. So, again the assignment statement is reached and y1 is increased to 2, added y1 is, you add 1 to the value of y1 and subtract x2 from y2, that is 6. Again the control reaches the point, test point, and the same thing holds. So, you add 1 to y1 and subtract x2 from y2. So, now this is the value. Now, when the control reaches the test point, you know that y2 greater than or equal to x2 is not satisfied. So, you have to take the false exit, and in that case z1 will be assigned the value 3 and z2 is assigned the value 1. Now, what does this program do? It divides x1 by x2, okay, and the quotient is given in z1 and the remainder is given in z2. So, z1 gives the quotient you are divide x1 by x2, and z1 gives the quotient s2, z2 gives the remainder. This is what the program does. Now, we know that this is correct. It is a very simple program. We can easily see that this works correctly. But how do we technically prove that it is correct, and how do we make use of predicate logic for that? The flowchart program in the figure which you have just seen performs the integer division x1 by x2, where x1 is greater than or equal to 0 and x2 is greater than 0. You cannot divide by 0. So, x2 has to be greater than 0, yielding a quotient z1 and a remainder z2. That is, z1 is the quotient when x1 is divided by x2, and z2 gives the remainder when x1 is divided by x2. Here the input variables are x1, x2, and they are pairs of integers, non-negative integers. Y bar is again y1, y2, they are again pairs of integers. Z bar is again z1 is an integer, z2 is an integer. So, in this case the input domain, program domain, output domain, they are all pairs of integers. They are all the same in this particular example. Now, there are two aspects to proving a program works correctly. One is partial correctness, other is termination. One is partial correctness, other is termination. Now, what is this? Generally, when you have a program, you have what is known as an input predicate which satisfies some conditions. The input should satisfy some conditions in the beginning. Then when the program is executed, there is an output predicate which tells you the relationship between the inputs and the outputs. And so, when you start the program selecting an input which satisfies the input predicate, finally, when you reach the halt statement, the output predicate should be satisfied. This is what we want. Now, in the partial correctness portion of it, you are not bothered about termination. What you say is, given the input predicate, if the program is executed and you reach the halt statement, the output predicate is specified. You are not going to worry about whether it is going to halt or not. Whereas, in the second portion, termination, you have to worry about the termination of the program. So, given an input predicate, you have to show that the program will ultimately terminate for that particular input value. So, in order to prove the program is totally correct, total correctness, you have to prove both parts, partial correctness and also termination. Let us see how we do this. Just for explanation, see what is an assignment statement, how the variables are replaced. y1, y2 is 0, x1 means y1 is replaced by 0 and y2 is replaced by x1. Similarly, y1, y2 is replaced by y1 plus 1, y2 minus x2 means that y1 is replaced by y1 plus 1 and y2 is replaced by y2 minus x2. In general, we use the notation y1, y2, yn is replaced by g1 x bar y bar, g2 x bar y bar, g3 x bar y bar and so on, to indicate that the variables are replaced by the corresponding values. Simultaneously, all the gi's are evaluated before any yi is changed. For example, if y1 is 1 and y2 is 2, the assignment y1, y2 is y1 plus 1, y2 plus y2 will yield. First one, y1 will be increased by 1 value. So, the new value of y1 will be 2 and okay, let me explain with an example. Suppose you have y1 is 1, y2 is 2 and I have y1 comma y2 replaced by y1 plus y2, y1 plus 1, suppose it is like this. y1 will be replaced by y1 plus y2. So, the new value of y1 will be 1 plus 2, 3 and y2 is replaced by y1 plus 1, that is 2, like that, 1 plus 1, 2, like that. The verification of a flowchart program depends on two given predicates, a total predicate phi x bar over dx bar called an input predicate, which describes those elements of dx bar that may be used as inputs. In other words, we are interested in the program's performance only for those elements of dx bar satisfying the predicate phi x bar. In the special case where we are interested in the program's performance for all the elements of dx bar, we shall let phi x bar to be just true. That is, phi x bar is true for all the elements of t x bar. Then you have an output predicate which relates x bar and z bar. A total predicate psi x bar z bar over dx bar into dz bar called the output predicate, which describes a relationship that must be satisfied between the input variables and the output variables at the completion of the program execution. Again, as I mentioned to you, what is partial correction, what is termination, you have to see. You say that P terminates over phi if for every input psi bar such that phi psi bar is true, the computation of the program terminates. P is partially correct with respect to phi and psi if for every psi such that phi psi bar is true and the computation of the program terminates, psi psi bar P psi bar is true. P is totally correct with respect to phi and psi if for psi bar such that phi psi bar is true, the computation of the program terminates and psi bar P psi bar is true. That is, in the termination portion, if the input predicate satisfies some condition, the program terminates. In the partial correctness, if the input predicate is satisfied and the program terminates, you are not bothered about that, you assume it is terminates, then the output predicate will be satisfied. Now, it is totally correct if both these conditions are satisfied. Given a value psi bar which satisfies the input predicate, the program will terminate and the output predicate will be satisfied. So, in this particular example, let us see what are the input predicates and output predicates. Okay. We have to take the, actually in this case x2 cannot be 0 because you cannot divide by x2. So, the input predicate will be x1 greater than or equal to 0 and x2 greater than 0. This has to be the input predicate. And the output predicate should relate the output variable and the input variables. So, what is that? X1 is the number you are going to divide and you are going to divide by x2 and the quotient is z1. So, z1 x2, the remainder is z2. So, this relation should be satisfied by the outputs. Not only that, the remainder should be less than the divisor. So, z2 should be less than x2, because it cannot be negative, it has to be greater than or equal to 0. So, these two conditions should be satisfied when the program terminates. Now, first we are considering partial correctness. When you consider partial correctness, even if you take x2 greater than or equal to 0, it is okay. Only for proving termination you require it should be greater than 0. So, let us first prove partial correctness, then we shall prove termination, and then because we prove both the parts, we will be proving total correctness. So, first we shall consider partial correctness. Here we take the input predicate phi x1 x2 to be x1 greater than or equal to 0 and x2 greater than or equal to 0. Actually, for the total program x2 has to be greater than 0, but for proving partial correctness, even if we take as x2 greater than or equal to 0, it is okay. Now, look at the way the program works. You have to divide the program into paths. Now, the portion 1 to 2 is taken as one path, 1 to 2, is taken as a path alpha and the portion 2, 4, 5, 2 again that is taken as another path, and the portion 2, 3, 6 is taken as another path gamma. So, the loop is taken as 2, 3, 4, 5, 2 is taken as a path beta and 2, 3, 6 is taken as a path gamma. Now, for each at the point of the loop, that is at the point B, you must attach a predicate which is called an inductive assertion, and that should bring out the relationship between the input variables and the program variables when the control reaches at that point. So, now at B you define an inductive assertion P x1, x2, y1, y2, and what is that? It should bring out the relationship between the program variables and the input variables, and in this particular example it is what is y2? Initially it is x1 and you keep on decrementing it, isn't it? So, y2 is equal to y1 times x2 plus x1 is equal to y1 times x2 plus y2, and that is you have subtracted x2 from x1 a finite number of times and the remainder portion is y2, and y2 should be greater than or equal to 0. This is the condition which should be satisfied by the program variables and the input variables when the control reaches the point P. This is the inductive assertion. Now, taking this, we have to form verification conditions for each path. Verification condition for each path, and we have to prove that it is correct. Now, look at the path alpha. You initially, before you have that y1, y2 is replaced by 0 x1. What is the input predicate? Input predicate is x1 greater than or equal to 0 and x2 greater than or equal to 0. If this is true before this statement is executed, what should be true at this point? That is what you have to write. At this point y1 takes the value 0 and y2 takes the value x1, and the inductive assertion at this point is P x1 x2 y1 y2, and replacing y1 by 0 and y2 by x1, what is that? So, this should imply P of x1 x2 y1 y2, but y1 y2 at that point is 0 and x1 because of this. So, this is the first verification condition, and if you replace it, what is this? This is, if I expand this, what does that become? It is x1 is equal to y1 is 0. So, it is y2 is x1. So, it becomes x1 is equal to x1, and what is y2? y2 is x1 greater than or equal to 0. So, this is the first verification condition, x1 greater than or equal to 0 and x2 greater than or equal to 0 should imply x1 is equal to x1 and x1 greater than or equal to 0, which is true. So, this is the first verification condition and that is proved. Now, at the point consider the path beta. Initially when you start, what is the value of p x1 y1 y2, the input predicate, the inductive assertion? It is x1 is equal to y1 x2 plus y2 and y2 is greater than or equal to 0. Now, if you execute the path, y2 greater than or equal to x2 evaluates to true. So, you also have the condition and y2 greater than or equal to x2. So, this should imply the value after the assignment is made. The second time the control reaches B, what will be the inductive assertion? The values of y1 and y2 will be changed by the new values y1 plus 1 and y2 minus x2. So, the new value should be x1 is equal to, now y1 is changed to y1 plus 1 and x2 plus what new value of y2 is y2 minus x2 and what is the new value of y2? y2 minus x2, that is greater than or equal to 0. Let us check whether it is true or not. Now, if you simplify this, what will you get? You will again get this, because this x2 will cancel with this x2 and so you will again get y1 x2 plus y2. So, this portion reduces to x1 is equal to y1 x2 plus y2 and y2 minus x2 greater than or equal to 0. Now, we can see that this is the same as this. Okay. This is the same as this, and because y2 is greater than or equal to 0 and y2 is greater than or equal to x2, obviously y2 minus x2 will be greater than or equal to 0. Because y2 is greater than or equal to x2, you know that y2 minus x2 is greater than or equal to 0. So, this implies this. So, the second verification condition for the path beta taking you from B to B along 2, 3, 4, 5 and again back to 2 is also verified and found to be true. Now, consider the path gamma, which is from B to C. And here when you start, what is the inductor at the point B, what is the condition that is satisfied? x1 is equal to y1 x2 plus y1 x2 plus y2, this is the, and y2 greater than or equal to 0. This is the condition which is satisfied. And when you reach the point C, what is the relationship? The relationship between Z1 and Z2 which should be satisfied, the psi value which should be satisfied is x1 is equal to Z1 x2 plus Z2 and Z2 is greater than or equal to 0 and less than y2. This is the condition that should be satisfied. Now, before coming to the point, you make the assignment Z1 as y2, the new values are you are giving to Z1 and Z2. So, instead of Z1 and Z2, I can write y1 and y2. So, the third verification condition is x1 is equal to y1 x2 plus y2 and y2 greater than or equal to 0, and you are taking the false path, that is y2 less than x2. This is the condition which should be satisfied, and this should imply all this together. This should imply the psi, but now you know that at the last step you replace Z1 by Y1 and Z2 by Y2. So, instead of Z1 and Z2, the new values, the latest values of Y1 and Y2 I can use. So, this should satisfy x1 is equal to y1 x2 plus y2 and 0 less than or equal to y2 less than z2 less than or equal to, this is it should be less than x2, the divisor. So, x2. Now, you can very easily see that this is the same as this, and this one you can split as, actually the combination of these two gives you this, right. The combination of these two gives you this. So, this is the verification condition for the path gamma, and that is also found to be true. So, you know that the program is partially correct, that is whenever it terminates the output predicate and the input predicate, whenever it starts with the variable satisfying the input predicate, finally when it goes to the halt statement, the output predicate is satisfied. It performs the integer division which you want. Okay. We have seen what is the input predicate and output predicate and so on. So, with respect to this, this is the partial correctness, this is the input predicate, this is the output predicate. Now, the inductive assertions method, how do you go about proving the partial correctness? For a given flowchart program P, an input predicate phi psi bar, an output predicate psi x bar z bar, apply the following step. You have to cut the loops, we have cut it from B to B again. Find appropriate set of inductive assertions. In this case, at the point B, we attach one inductive assertion. In general, if the program is more complicated, you may have to attach at every cut point one inductive assertion, and so several inductive assertions you may have to write. Those inductive assertions should bring out the relationship between the program variables and the input variables when the control reaches at that point. Construct the verification conditions. So, here we have constructed the verification conditions for the path alpha, for the path beta, and for the path gamma. If all the verification conditions are true, then P is partially correct with respect to phi and psi. This is for termination. Okay. Now, the second portion we have to consider, let us take the same flow chart and consider termination. For proving termination, in this particular example, you have to start with the phi dash, which is x1 greater than or equal to 0 and x2 greater than 0, because you know that when x2 is equal to 0, the program will not terminate, you cannot divide by 0. With respect to this, you have to show that ultimately the program will terminate. What you do here is you attach a partial function u x bar y bar at the point B, and in this case it is the function is just y2 here, and y2 should take values from a well founded set. A well founded set, we have not yet studied what is reflexive and so on. It is a well founded set is a set with an order relation. For example, here it is less than, and here it is a set of non-negative integers with the less than relation, and it satisfies three conditions. It is irreflexive, antisymmetric and transitive, and every sequence has a least point. In fact, here if you take n and less than, if you take any subset of n, that will have a least element. Such a set is called a well founded set. Now, y2 should take values from a well founded set, and you should show that the control reaches the point B and the loop is executed and you go to the point P again. Now, the point is at this, when you go from B to B, the value of this is reduced. So, the first time you go here and the second time you go here, the value should decrease, and because you cannot have a infinite decreasing sequence, there is a least element. So, at some point you will get out of the loop. The main point to prove here is that if a loop is executed, ultimately you will get out of the loop. So, in this case what you have to prove is, at this point you must have a partial function like this. In this case it is y2. Now, let us take what are the values of y2, if by taking the example x1 is equal to 16 and x2 is equal to 5. Now, y2 was initially 16, next it became 11, then it became 6, then it became 1. It kept on decreasing. The first time the control reached B, it was 16, next time 11, next time 6 and so on. This keeps on decreasing and it has to take positive values only, and so at some point you will get out of the loop. This is what is meant by termination. So, you prove that the program terminates. Not only that, usually termination, for proving termination, you attach good assertion at that point, like verification condition. Here also you have good assertions, and in this case it can be, say, y1 greater than or equal to 0 and y2 greater than 0, something like that, greater than or equal to 0 you can say. So, these are good inductive assertions which should be satisfied at the point where you cut the loops. They need not bring out all the relationship between the input and the output variables, but they should satisfy some conditions. So, you can have something slightly less effective, like you can just have y1 greater than or equal to 0, y2 greater than or equal to 0, something like that at that point. But the point is, you must attach a function u x bar y bar which takes continuously lesser and lesser values from a well founded set, and so ultimately you will exit the loop. That is what we want. The program will terminate. That is what we want to prove. Well founded sets method. This is the method for proving termination. For a given flowchart program P and an input predicate phi psi bar, apply the following steps. Cut the loops. Here again we have to cut the loops and find good inductive assertions. So, here we say good inductive assertion. There must be some assertions, but these assertions need not bring out all the relationship between the input and the output variables. And now, choose a well founded set and good partial functions. The function which we defined here is a good partial function. What is a good partial function? When you start from a point and after executing the loop you reach the same point, it should keep on decreasing. Choose a well founded set and good partial functions. If all the termination conditions are true, then the P terminates over phi. What are the termination conditions here? The termination condition here is the first time you have q x bar and y bar, and after execution of the loop, the new values, if I say, this should be greater than or equal to the new value x bar dash and y bar dash. This is the initial value, and this is the value after execution of the loop. So, it should keep on decreasing like that. So, if you want to prove total correctness of a program, you must prove both partial correctness and termination. So, only when you prove both, the program is totally correct with respect to the input predicate you have specified. Here in this example, when you want to prove total correctness, you must not take this, you must take this, because the earlier one it will not terminate. So, with this input predicate, the program is partially correct, it also terminates. So, it will be totally correct. And what is the output predicate? The output predicate brings out the relation between the input and the output values. In this case, it is x1 is equal to z1 x2 plus z2, the quotient and the remainder, and the remainder is less than x2, but it is a positive quantity. So, this is the one. But you see, there is no automatic way of writing the inductive assertions. You have to think what the program does at that point, what are the conditions satisfied by the input and the program variables at that point, and right. So, for a small program you can do that, and you can write all the verification conditions and termination conditions, etc. For if the program is very big, you know that this is going to take a lot of time, and so you resort to testing rather than proving programs correct. And testing, how do? You give proper input values, thinking that these are the possible values, and then if the program run the program, and if it gives the proper output values, you assume that what you have done is correct, the program you have written is correct. But the correct way of going about any program is you have to prove that the program is correct. But for practical purposes, when the program is very large, this may not be possible. But still, this way when we have proved, it tells you the use of logic, the use of propositional logic, the use of predicate logic in proving that the program is correct. Okay. So, logic is the basis of computer science, and this tells us how it forms the basic in writing programs and proving programs.